Section 9.3 is polar coordinates, and this is essentially a review section from what you might have done in trigonometry prior to this class. We'll graph polar equations and polar curves, and we'll convert polar equations to Cartesian equations, plot polar points to start with. Ultimately, we're just reminding ourselves how to work between polar and Euclidean coordinates. Now, polar coordinates are specified by an angle theta and a radius r. So if we recall that we let what used to be the positive x-axis, we'll call it the polar axis now, and then we'll sweep out or subtend an angle of theta degrees. And then if we specify this angle of theta degrees and then a radius, a distance from the pole being what used to be the origin, then we can arrive at a description of any point in the plane. So polar coordinates are specified by an angle and a radius, theta and r. They're written r theta, which is a little bit deceiving because it looks like r sometimes is the independent variable. But they're in no way connected to xy in the sense that, when you plot an xy coordinate, you move a distance of x along the x-axis, then a distance of y vertically, and then you plot your point. However, with polar coordinates, you sweep the angle, and then you move out the distance r. Now also remember that a negative value of r, we would sweep out the angle, and we'd move the opposite distance r from the origin, or from the pole. So to convert a polar coordinate to Euclidean, we have the following identities. X is r cosine theta and y is r sine theta. Now that should be easily seen from this right triangle. If we plotted the point xy here, then we can see a right triangle, the distance along the x-axis, distance along the y-axis, and then the hypotenuse is r, which is coincidentally the distance from the pole to this point. So that's a suitable radius value to use. Now, x squared plus y squared equals r squared. So this is one of our useful identities in this situation. The Pythagorean theorem gives us that. Similarly, we've got that with this being an angle of theta, the sine of theta is y opposite over hypotenuse r. So y over r. So sine theta equals y over r. If we solve for y, we have that y equals r sine theta. Very similarly, we look at x and y, that's adjacent over hypotenuse. X over r is equal to cosine theta. So x equals r cosine theta, and we get this identity. So really, all of this information right here can be gleaned from this right triangle. So it never really needs to be remembered in terms of these formulas here. The last is that theta, the tangent of theta, is the opposite y over adjacent x. And this might be useful to help us find the angle theta if we're given xy coordinates or Euclidean coordinates xy. Now, let's work with one of these points. They ask us to convert the point 2, -2 root 3 from rectangular coordinates into polar coordinates. And then they want multiple cases here, such that in each of these cases we have a different different condition to satisfy. So xy is 2, -2 root 3. So we have an x value of 2, a y value of -2 root 3. So the first thing we can do is determine what r is using the Pythagorean theorem. So doing so, we get r is the square root of x squared plus y squared. So we'll substitute these two values in. We get this line here. Simplifying that, we have 4 plus 4 times 3. It's root 16. And root 16 is 4. So r, our radius, is 4. This point is a distance 4 from the origin, or a distance 4 from the pole when we think about it in polar coordinates. So we know the first half of a polar coordinate. We know what r is. In this condition A, they want us to express the point with a positive radius. So it turns out in polar coordinates that we can express points in non-unique ways. That's different from rectangular coordinates, where we can only express the point 2, -2 root 3 as that, modulo some maybe arithmetical differences. For instance, 2 could be written as square root of 4, but that's not really very different. Now, these are fundamentally different representations that we can have in polar coordinates, and we'll see that by the time we're done with these 3 parts of this example. So anyway, they want a radius that's greater than 0, and we found that, positive 4, so that's good. And then they want the angle to be between 0 and 2 pi. Okay, so our second component, theta, needs to be an angle between 0 and 2 pi. Well, let's work on finding any angle that corresponds to this point. So that's where we use our tangent formula and ultimately an arctangent. We have that tangent theta is y over x, so it'll be negative 2 root 3 over 2. And that's exactly what we have here. We get negative root 3 out of this. If we think about which angle theta gives us a tangent value of negative root 3, then we could recall that that's negative pi over 3. If not, we might need to write this as negative root 3 is negative root 3 over 2 divided by 1/2. We just multiply by 1/2 in the numerator and in the denominator. That's a form of 1 to change this. Now, what happened outside? Well, tangent theta, we rewrote theta as arctangent, both sides of this equation, to get that theta is equal to arctangent of negative root 3. And this might be more helpful to find what this angle value is. Sine has a value of negative root 3 over 2. Cosine has a value of 1/2. If we look for an angle where we put this minus sign down here, then we'd realize that we're outside of arctangent's range, or domain rather. So it would be a value that we couldn't, that we could not plug in or evaluate from arctangent. It's not arctangent's domain; it's arctangent's range. Let's let's evaluate this thing anyway. So we've got this is the angle negative pi over 3. So recall that negative root 3 over 2 is in 1/2 is approximately here, quadrant 4. Remember that arctangent gives us a value between negative pi over 2 and pi over 2. So that's the range I was talking about before. We would be outside of arctangent's range if we considered a negative cosine, because that would put us over here in quadrants 2 and 3. So this makes sense that we're in either quadrant 1 or quadrant 2. So anyway, that's negative pi over 3. And that is a value that will work. We could fully express this point as 4 comma negative pi over 3. And that's exactly what we do here to write it down. But then we realize that we need to change this angle value. Well, remember that any 2 pi rotation of an angle theta is going to land us at a coterminal angle. So if we realize that this is negative, we just start adding copies of 2 pi to it until it's positive. So the first time we do that, we end up with 5 pi over 3, and that's a positive angle. It's also between 0 and 2 pi, and we have exactly the expression for this angle that we're looking for. R is positive, theta is an angle between 0 and 2 pi. Specifically, it's positive versus being negative. So then the second one, we want an angle r that's less than 0. We want to express the radius as, a radius r that's less than 0. And we want an angle between 0 and 2 pi. So now if r is less than 0, we'll just go ahead and, well, we want to express r as being less than 0. We just put a minus sign in front of that number. But remember what that does in polar coordinates is it flips our point 180 degrees from where it was, or pi away from where it was. So if we were pointing down here, or let's say down here for this point, if we have a negative radius or make the radius negative, now we're talking about a point over here, exactly opposite on the other side of the pole from the initial point. So to do that, we need to fix this angle to make sure we're still in the same place. Well, if we need the angle to be between 0 and 2 pi, we realize that 5 pi over 3 is greater than pi. So we just subtract a copy of pi to correct for the fact that we were at, that we've changed our sign from positive to negative 4. And our new angle, our new point representation is the exact same point as this, only it's written as negative 4, 2 pi over 3, negative radius, and a positive angle between 0 and 2 pi. These are coterminal points. They're in the exact same place in the plane. We'll see that when we graph them in just a moment. Let's move on to part C. Part C says a positive radius and an angle between -2 pi and 0. So we go back to writing 4 as being positive. Then we would think, well, we had exactly that up here. And we could write this down exactly as we see it. If we didn't already have that, we could take this one and say, okay, this is our polar representation of this curve, or one of the polar representations of the curve. Let's just subtract 2 pi from it. Well, when we do that, we get right back to -pi/3, and that would be what we come up with. Okay, so let's plot this point. So remember that so we have the point 4, 5 pi over 3. And it's best to do the angle first, then handle the radius. 5 pi over 3, well, we can count that out as 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3 to get to here. That's more or less correct there. So 5 pi over 3, we're in quadrant 4. So we've marked out our angle, and now our distance is 4 from the pole. So then we move out 4 units, 4 radial units out to this point 4, 5 pi over 3. Then we have our point plotted in its first representation. Now let's make sure that those other 2 points we found on the previous page are still in the same spot. They're coincidental with this point. Well, -pi over 3 is this angle, down from the polar axis, or what used to be the positive x-axis. And +4 is the distance out, so we move down this way and then out 4, and of course we're right here at this 4 -pi over 3 point. Next up, we've got -4 2 pi over 3. So let's deal with the angle first. 2 pi over 3 is this angle. So when we move away from the pole, we have a -4. So rather than moving this direction, we have to move this direction away from the pole. So we'll step 4 units away from the pole in the opposite direction. And that's how we arrive at -4 2 pi over 3 and the same point as the other 2 representations. So these are all the same point in the plane, and that's why. It's really important for students to understand this basic plotting concept. A lot of students might fumble their way through and just get enough right to not worry about it again. But if you don't understand why these points are the same and how to plot these points and manipulate them, then you're never going to understand polar graphs. And it's important to understand polar graphs so we can do calculus on them. Before we get there, let's do some work with Cartesian coordinates, finding a Cartesian equation from a polar equation and vice versa. The first example is to find a Cartesian equation given this polar equation. So always keep an eye out for tricks that might help. In other words, squaring things and adding things up for Pythagorean theorem. That might work, especially when we're dealing with sines and possibly cosines in here. Otherwise, we'll just keep an eye out for 3 sine theta is pretty close to, r, or x equals r sine theta. Problem is this doesn't really fit. So there are some tricks we can do. We could go over here and say, okay, well, I remember this is a useful thing, only r is not in the right place, so maybe I can't quite use that. Now this is nice, but I don't have anything squared at the moment. Maybe we'll have an idea come from this. This is probably going to be more useful to go from Cartesian coordinates to polar than the way that we're trying to go. So let's keep an eye on these centered too. Notice that if I multiply both sides of this equation by r, I'll get an r squared on the left, and I'll have r sine theta on the right. R sine theta is y, and r squared is equal to this x squared plus y squared. So that's the trick here. Multiply both sides by an r to come up with this equation so that r sine theta becomes y, and r squared becomes x squared plus y squared. Now move the 3y over to join all the variables, and we realize we have x squared is pretty much packed away. It looks like this thing might be a circle. We'll find out shortly. But we have minus 3y after y squared. So we need to try to factor this. So what I'll do is take half of negative 3, it's negative 3 halves, square it, and that's 9/4, and I'm completing the square. I add 9/4 to both sides of the equation since I have an equation. So I haven't changed anything ultimately. And then I can factor this y squared minus 3y plus 9/4 as y minus 3 halves. If we keep track of this object, we know this thing always factors in this way. So this is our factorization here, and we see that, yes, this is in fact a circle. It has center 0, positive 3 halves, and it has radius square root of 9/4, which is 3 halves. So we have a circle with center 0, 3 halves, and radius 3 halves. Next up, find a polar equation for the curve represented by the Cartesian equation given. So we have 4y squared equals x. These are quite a bit easier. All we have to do is say y is r sine theta, x is r cosine theta, and see if we can solve for r before we're done with this. Well, it's a pretty straightforward process to solve for r. Note that when we get here, we have cosine over sine squared theta with a 1/4. Cosine over sine, cosine theta over sine theta is cotangent theta. There's an extra 1 over sine theta, so that's cosecant theta. And we arrive at this polar representation of that Cartesian equation. So this is usually the easier direction. It takes fewer tricks. We just, everywhere we see a y or an x, we plug in r sine theta or r cosine theta respectively. So let's graph 1 before we're done with this section of the notes. We're asked to graph the curve y equals 6 cosine theta. Now, by the time we're done looking at these polar coordinate graphs and equations, we should be able to classify what we're about to graph from up here. So we should be able to look at that and know what it is by the time we're done. Let's start slowly and learn this though. So we just saw that for something similar to this, r equals 3 sine theta, we got a circle. In this case, we've got r equals 6 cosine theta. So this might be a circle, and since we can already see it, we know it is. But let's see possibly why. Now, I take a bunch of angles as my independent variable, and then I'll find the radius r based on this equation, r equals 6 cosine theta. Plug in 0, cosine 0 is 1, so we get 6. Pi over 2, cosine of pi over 2 is 0, so we get 6 times 0 is 0. Cosine of pi is negative 1. 6 times negative 1 is negative 6. Cosine 3 pi over 2 is 0. Cosine 2 pi is 1. We're right back here. So let's see where these points are on this curve. It might not be very informative to us, but I'll try to convince the reader to fill in the details. So at 0, angle is 0, we're here. Remember to plot these as polar curves. They are not Cartesian. So angle 0 is along the polar axis. We're a distance 6 away, so we're at this point to start. Now, pi over 2. We sweep to pi over 2. It's along this angle, but our radius is 0, so we're a 0 distance from the pole. Now, pi negative 6. This is an angle out here. Pi would put us here, but since we got a negative number, we have to reflect it back this way, to the right. So we end up plotting the point at the same place that our first point was. So 6, 0 is coterminal with negative 6 pi, or coincident with negative 6 pi. And then when we plug in 2 pi, cosine 2 pi is 1. So, 3 pi over 2 is the next one to do. When we get to 3 pi over 2, we're looking along this angle, but cosine 3 pi over 2 is 0, so we're right back here. Now, what we're missing is the fact that, I've drawn in the rest of these points when we don't actually see those. So the way to actually see those is to do the points between 0 and pi over 2. In other words, those common angles of pi over 6, pi over 4, and pi over 3. And then what you'll see is that roughly as you graph these, you'll get something like this point here, here, and here. And you pick up these 3 and you convince yourself a little more that this thing is actually a circle. When you do the same for the second quadrant, you'll find that the angles are here, here, and here. And the reason that they're there is because when we sweep through the second quadrant, cosine's negative. So it's reflecting all three of the points that you would have had up here down here. So you'll note that by the time we get to pi, from 0 to pi, we've formed the circle fully then. That's true, that's the case. Now, if we go from 0 to 2 pi, we just repeat. It just draws over itself. It does a second lap through there. And you can confirm that by doing points in the third quadrant here, which should reflect to these points here when you plug them in. That's looks like a 7 pi over 6, 5 pi over 4, and 4 pi over 3 would be those 3 points in there. And you'll see that the cosine will be negative, so you'll have to reflect back to quadrant 1. Now in quadrant 4, cosine's positive, so we get these 3 points here exactly as is. And what we'll have done is lapped around this circle 2 times by going from 0 to 2 pi. Now the circle is very closely related to Lima solids, and we'll see that in the supplemental graphing video that I'll do for this section. The rest of these, we'll still graph them by hand, and that'll be the next video. But in the end, I'll do a third video to do a full look at all of these polar coordinates with a graphing calculator. You should be able to do them by hand. That way you'll understand the calculus that we're going to do with them. If you don't know how these things work by hand, then you're going to be at a complete loss for finding areas in them or arc lengths in them. So stay tuned for the next section and then the supplemental graphing section after that.